Alright, I'm showing you guys one of my favorite games, which is Shenzen IO. I've already completed a bunch of these challenges. Again, I enjoy it. And I want to show why. Alright, so most of this chat you can just ignore. I mean, unless you like backstory or you get something like undocumented instructions, which I won't go into right now. Alright. Oh, can you keep a secret? Haunted doll, blah blah blah. So yeah, it's probably not that important. We'll find out if it is in just a second. So just want to into jump into the challenge. So it's a puzzle essentially, but it's very similar to the kind of microcontroller um, electronics development that happens in real life. Like it's not exactly the same, it's not one for one. You're not going to get a job because like you're like, hey, I got a high score on Shinzen IO, but it will prove your ability. It will maybe not even improve, depending on where you're at in electronics. It will get you to understanding the mindset of electronics, at least modern electronic stuff. All right, so let's see here what we got. Random is an input as a simple input connected to a random number generator speaker, which is over here. In the speaker, we can't move. We just trace to it. This, yeah, okay, we can move this around. Um, when value of 1 is randomly generated, play sinister giggle sound effect. When value of 2 is randomly generated, play blood curdling cry sound effect. Look at supplemental data of the manual for audio data that Carl found for his thing. All right, so I'm guessing. Um, I wonder. So I'm guessing this is the random number generator, and I'm assuming that all the outputs generate stuff, the same kind of stuff. We're going to kind of test that. What's the best way to testing this? Um, oh wait a minute. So yeah. It's an interesting one. Let's go ahead and throw this on here. That's interesting. Usually it's crying that's the wrong type of input. Um, let's step it. All right, so here we go. We got an 86 out of that. Um, 50, 36, 91. All right, so this is where our input's coming from. We don't know what the other pins are doing. I'm pretty sure that's the case if we, yeah. All right, so, we can throw that away. This is the important chip, important pin that we're gonna need to connect. There we go. Um, Next thing, all right, so there's some supplemental data that we'll get to in a second. But only when gets to when a value of 1 or value of 2 is weird. All right, so the value of 1, in fact, like it says like there's a supplemental information, and the game does come with a PDF, which is pretty cool that you can actually print out, put into a binder, have dividers and all that kind of stuff. But we could also just look at the signal and see like, okay, this is the output. Wow, that's a crazy output. For when there's a 1, this is, I'm assuming when there's a 2, it has an output like this. All right. So I'm probably go. Like normally I would just be okay. I just produce this output, but and maybe I have to, but maybe the supplemental data will actually give me more information. Since it's a lot of output, I'm going to just throw this in here. So this is going to be things that create the output. Um, I don't need to be that long. Just slap that over there. Slap that over there. Boom. All right. So these are going to be our sound generators. Then we're going to need a thing that tests the input and then generate determines which one of these to engage. Let's see, does this have enough? All right, we got P0, we got two X things. All right, so we'll come over here, hook up this one. That actually goes there, and boom, like that. All right. So that's kind of like my overall idea. This is going to be testing PO, P0, the information from the random number generator. And if it's 1, I'll trigger X0. And if it's 2, I'll trigger X1. And then these will play a pre-recorded sequence. And the nice thing about this puzzle is that there's no one right solution. I could possibly store the information in some memory module and have it like just pull that memory and play it up and play certain data set if it's a 1 or another data set if it's 2. But this is like my little prototyping phase. So what we need to do is sleep 1. I always begin with sleep because when you're writing this code's going to be continuously looping, which is very similar to a lot of embedded systems. So when you're dealing with microcontrollers, often you might be dealing with an operating system, but often you're just going to be dealing with a loop. Especially the smaller the chip is, the more likely you're just going to be dealing with complex loops. And so this part is we're going to sleep for 1 second, and then we'll do a spur of activity, and then once we reach the end of the loop and it goes back to sleep, we'll go back to sleep a little bit. And so we'll then test if test equal P0 1, and if that's equal, then we will move 100 X0, and if not, we'll move 100 to X1. All right, and so that's our 2 triggers. Very small, doesn't really need to do much, and then after that, it's going to loop back to the first instruction, which goes to sleep and wait for the second for the next one. And that these clock ticks, it's a 1. I'm saying second. It might be microsecond, nanosecond, whatever. But basically, you're sleeping 1 clock tick. Think everything in clock ticks. So for clock ticks, when you have a your computer, I don't know if anyone cares about how fast their CPUs are going nowadays, because it's just incremental stuff. But back when I was first getting computers, you'd be like, oh man, my chip is 45 megahertz, or no, my chip is 60 megahertz. And the higher megahertz was really important because that's how many clock ticks a second you can do. Clock ticks are very important for how fast all these chips can go. So that's why I'm saying this is 1 clock tick and not 1 second. Because 1 second in microprocessing time is forever. Um, and I don't even know what the clock rate is on these systems. In fact, I guess it's variable because this is actually what's affecting the clock rate. Um, but when you're dealing with microprocessors, you want to think in clock cycles or clock ticks, and you want to pay attention to what uh, the clock rate of your chips are. But anyhow, use that. In fact, we could start simulating. Oh, part not sleeping. Oh, block on right. Yeah, okay. Um, I need to set up. So now these are not going to be sleeping at clock tick. These are going to be sleeping. Uh, they are. I gotta pull up the instructions again because I forget. Is there a button for the instructions? That'd be nice. PDF that comes with the game. All right. Data sheets. There we go. That pulls up a thing in my browser. Because I forgot the sleep instruction for waiting till we get input. So, and these instructions aren't a known assembly. Um, they're just their own system for this game. Uh, here. So that's why you actually have to read the language manual, which is something that we do in real life when we program stuff. Um, all right, program structure, labels, conditions, register instructions. All right, there's, yeah, okay. Sleep X. All right, SLX, X0. So this is going to sleep until something happens on the X0. And then I need to move the information off the X0. I'm going to move it to the accumulator. And then same thing here. SLX, X0, move X0 to HCC. This clears the buffer. Oh, that's my problem. I am doing this for every other thing. No, I need to separate this to that's equal P0 2. All right. And so yeah, there we go. We see difference now. It's not just constantly pinging this. It pinged this once and it pinged that second time. So we did a quick test of this chip and we found a bug. We went through and we fixed that bug up really quickly. So we're not solving the puzzle yet, but we just solved a chunk of it. So now we go over here and start outputting what we need to put out. All right. So let's see here. All right, so 180, 41. All right, so again, that line there is just to get the information off the line, clear that line, so that way this chip is not blocked when it tries to write to it again. And now we're going to move 100 P1, sleep 1, move 80, and then 41, 80, P1, move 41, P1, and everything sleeps in between all these. And yeah, I'm already seeing like I do not have enough instruction space for all this. Not with all the sleeps. I'm going to need to pull from a memory bank. And we'll get to that. I actually have not come across a challenge yet which required me to do that. Okay, so this one we could uh, save a little time. B1, and we could sleep 2 clock ticks. So, and then back to 41, and then 61, 69. All right, move 41, B1. Let's see here, 69, 74. All right, I got two lines of information. Now, this is the part that's not totally realistic. Is that in this game, you have only so many lines per chip in which you can write. But in microprocessors, you only have so much memory that you can store instructions in. So it's similar, but not the exact same. And usually, chips have way more than just a dozen, uh, you know, bytes of or a dozen lines of instructions that you put in there. What was after 41? 69. 69 P1. Sleep one. I don't even need to sleep one there because it's just going to loop after that anyhow. I just can't put anything else in there. So, but at least we'll see, like, it'll get to a good point and then it'll fill out. And then we could test out. All right. So, why is this red? It should not be. Oh, should I put 50? Okay. That's okay. Yeah, we can hop this around. Here's what we're gonna do. So the problem is we need to output of if these things aren't triggering. Oh man, I need output of 50. So the quick thing I would say to do is that we connect that to basically. So this is kind of like a trace, but it jumps over another trace. Normally you'd like use a via, and then via would get you to the other side of the board, and you draw a line. But this is something else you wouldn't normally see in actual microelectronics. But we can do that. And so here's what we're going to do. So I'm now adding more instructions so that if this condition is true, it's going to run that and then jump to the end. Before I had an implicit loop, now I'm having an explicit loop. Why? Because otherwise, oh man, no, I need to do something else actually. So I'm going to move 50 to P1. All right. All right. Let me see here. So actually, I'm going to. How many seconds do I got here? I don't know. Sleep 1, 2, 3, 4, 5, 6. So I'm going to. I need to basically generate a 50 signal when these conditions aren't met, which is what I'm trying to do here. But then I need that signal to disappear when I'm generating, when the conditions are met, I'm doing other things. let's see what happens. I don't know. This should not work in a normal thing, but all right. So yeah, it's kind of what I expected. Um, all right. So basically, what's happening is that we are always sending out 50 over here, and it's okay. Okay, I need to see. This is where my sleep is hurting me. Um, this is okay, but it only works when if the signal being sent is greater than 50. As soon as it drops under 50, um, the uh, the information is being overridden by 50. So rather than do some crazy stuff here, since I know I'm going to have to use the memory module, what we're going to do is create a new copy of this and uh, copy this for now. Um, New design. Throw that in there. Um, let's see here. I don't remember which one and see which. I think this is the one I want. All right. And I'm not exactly sure. I haven't used this one a lot, so. All right. This here. Put that here. Connect it. Uh, these are EXO pins. So, right. Oh, wait, no. All right. So that's right. A pins are addressing and the D pins are data pins. So we're going to need to set this up in a way. In fact, let's just pull out one of these bigger ones. They're more expensive, but they get things done better. All right. So now, like, boom. Now, we're going to extend it a bit so that way we can see the pin names. All right. Let's just do, yeah, we're going to run this one and see, yeah, this should work. 180, 41, 14, 14. We're going to need probably more chips here. 31, 69, oh, 69, 74, 54, 7, 19, 40, 75, 75. The last value is going to be 50. All right. so we are probably still going to need this tiny chip here. Just trying to figure out how we're placing on this. That's one of the things you're going to have to do in electrical engineering is you're going to have a lot of constraints. One of them is going to be the size. For instance, you have to make sure your card fits certain form factors. So I'm going to need probably two of these things set up, and then uh, one of these, and then of course this chip here. So we're going to drop this down here. Oh, probably not that far. All right. All right. We're going to have something I can do is I can put this over here. And then we could put another one. So this is where I'm going to have base issues. Arrange all this. All right. It's a bit more problematic than I thought. All right. Since this pin's dead, I could probably use that. And then, or, it doesn't matter. All right. So, step one, we've got things fitting on here. Step two, we loaded that one in. That's a good question. We got two outputs going to the speaker. If one's putting out 50, we're going to need something that says, hey, stop putting out stuff. All right, let's see how long this is as well. All right, it says 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All right, 3. All right, so they're both 13 notes. So I can have this thing here pump out 50 until we get something, and then leap for 13 notes. So sounds easy, hopefully. So let's take care of that first. We're going to do that. And that's why I call this end, because I can go down here, but this is the end. All right. and I might need more code space. So you know what? Let's get rid of this. And the reason I try the small one first is because larger ones mean more cost. There we go. That looks pretty enough. Good. P0. Move one. Okay. One. We're gonna move 100 to x2. That's this one here. Jump to the end. Maybe. Better yet, if test if less than, it's less than 3, then we are going to what am I doing? We're gonna call this start. If it's those do greater than 2, we are going to do move 50 to, I don't have P1 available. Oof. All right. How am I going to route this? All right. We're not going to have to worry about that right now. We're just going to see about getting the time things done. Small goals. All right. So it's greater than P0. Then we're jumping to the end. All right. Next up. Now it's either going to be 1 or 2. So if target equals our test equals P0 and 2, we are going to move 100 to, let's go x3. And jump to the end. And this, of course, is if not, we move 100 to x1 or x3, and then jump end. Well, not all. We're going to do a thing here called comment. I think that's comment line. Forget. Then 50. Sure. All right. We'll solve that problem later. All right. So this is going to be XLX X1. And for now, we're just going to move X1 to acclimator. Here, SLX X2, and move what? x2 though. So nothing impressive here, but so far no block. All right. Now let's see, this is x2 is, hopefully I get the right chips over here. Oh, I messed up here. All right, so this one should be x2. Check out the instruction set. Here, that's not. Anything for the memory chip. All right, so I should be able to say 0 to x1. Now put the address, and then move 0. Let's just add this. All right, p1, and then oh yeah, we're gonna need to do a loop too. All right. We're gonna do that so that we are freeze a break acclimator. All right. Move 0 to x1, move 0 to ACC. And start, we're going to say here, just greater than, let's say test less than ACC 14. I'll say ACC is under 14, and then boom, it goes there. So we go plus. If ACC is under 14, we go, we grab D1, which is connected to our X0. Move X0, have down here, P1, and then loop 1, in fact, this would be our loop, plus jump loop. All right. And then after that's done, it should loop back to start, which I guess I don't need to have a start thing, but let's see how this works. All right. Kind of good, kind of bad. We want to know why it's looping back here. Oh, we're not increasing the acclimator. That makes sense. So let's add ACC1. Too many operands. Why is that too many operands? Let's go see the. Oh, all right. I just have to do add one. All right, good. That ends the loop. Good. But now it's always spitting out 50. Shouldn't do. Why is it reading the last one? Maybe I should set that to 0. All right, good. That way it's not going to confuse with the other thing. Next part of the test is I need, in fact, one thing you'll see with the addressing over here, go grants. Right. And so you'll see the addresser for A1 is going to be this one. This would be the addresser for A0. But you'll see this, the addresser move one step per loop. I was off by one error. 13. But I like that it spits out 0 at the end. So we're going to keep it 14 right now. All right, and this one, we got 16, 36. In fact, actually, I can have it say, depending on the number, I can have it read from one message thing or the other, right? Yeah, I think that'd be a good one. Well, we got to store this number in here anyhow. Oops. 42, 14, 10, 58, 100, 76, 26. Where's that? 26, 28, 70, 80, 42. 0. All right. All right, that's that. We're going to cut this out right now. We're going to see about connecting these things together. I don't know. I don't like it yet. All right, so move this back here. All right. Again, for our, like at the beginning, we're just trying to solve the puzzle. We could get into refinement another time. Let's see here. The address bit is connected to X3. And then move x2. All right. Or not sleeping. Oh yeah, I need to. All right, so at least the sounds are working. All right. All right, so that part works. I'm gonna reset this. I think here. All right. We need to move certain things around. We need piezo. We need access speaker from here. This is going to be the painful part. Um, Maybe 5. Right. Again, we save our work by going back and duplicating that. All right. Go this over here. This over here. We may have to change some names. Right. We can go there. There. Tighten that up a bit. All right. Then there we go. We can output that to there. We can output that to there. All right. Ta-da. All right. One. Two. Pins aren't connected. All right. All right. See how that looks. Block on read. All right. Everything's terrible anyhow. All right. Target. This is greater than P02. Jump to the end. So jump to the end. Why is that chip running? What did I do wrong here? All right, we're sleeping for X1. Oh, X1's coming from there. We need to sleep on X2. All right. In. Oh yeah. Derp. And I got the ones wrong. All right. That's easy to fix. X1. X0. All right. So we have everything on here. We we have room for everything. Now we just need to move 50 to P1, and then jumps at the end. Otherwise, we sleep. I think 13 is the right number. Oh, that's right. There we go. Move 0 to P1. That should work. Ah, that almost works beautifully. All right. 12. All right. So why are we not looking at it here though? Let's do jump over there. All right. So kind of smooth that up better. All right. All right. Boom. That's the logic thing. All right. Now it gets to be the fun part. One second. So the way I look at this, so we solved the puzzle. We're good. If you only care about solving the puzzle, you go into the next puzzle. But if you are making, if you are working for a company, making these products, whatnot, you want to make sure that your product is better than your competition. So we see here, we are more expensive and we take up more energy than child industries. I don't care about lines of code. The only thing about lines of code is that if we had less lines of code, we might be able to go down to a cheaper chip, and that could help us out with that. Now, often there's a case where you have to choose: do you want to have cheaper setup or lower power usage? Sometimes you can get both. So what I do here is that I'll make two versions. All right, yeah. And now we got more challenges, all that stuff. We go back into here. We delete these other copies. Delete. We're gonna rename that one to solve. And then we're gonna copy that. And now we're gonna look at, all right, well, quick, run it again. Just so we can see our benchmarks. All right, power usage isn't too much. In fact, actually, I like checking out, probably going after the power usage first. To me, I feel that's easier than worrying about production costs or line of code. So we're going to do that. So we have the profiler, and this will show us where things are spending most of their time at. All right. Oh, that's one thing I should have done. Come over here, set a breakpoint. Now, so after the run, so half the time here it's looping through, and that makes sense because the thing's cycling through. So there's that. Over here, it's spending a lot of time here, and so one thing is sleep instructions don't cost you any power. The profiler is showing us where the time is being spent. It's not telling us exactly where the power is being spent. But if you turn this off, you can actually see that this is drawing 76 power, 76 power, and 147 power. So this is our more power hungry chip. I mean, it's kind of even across all these. Like if you, it's split between this chip and these two chips. Um, but this is probably where we're going to get our most power savings at. Let's see here. I'm not seeing. Yeah, I'm not seeing where we're going to do that. Oh, that's one thing is. Um, so if we could set it up where, like, once we set that we are sending 50 there, we can then stop sending 50 and it'll just keep sending it. So this will increase our lines of code. Again, we don't care about that because it fits on the chip. Only time that we care about, only thing we're reducing the lines is that we could go to a smaller chip and say it was like $2. Um, if we can remove one of these chips, like if we could combine this together, we can, save $5. That would be really good. But let's see here. So we're going to remove this line. Well, we kind of need it at the very beginning. We can get around that actually. There's a one-time instruction we could do. At the end of these, we can say move 50 to P1. Then I can say here, move 50. All right. So our beginning part won't work out, but yeah, at the end. And let's see here. Okay, it should. I don't remember what our old power usage was. That should drop the power a bit. Put it 42. That's weird. I'll investigate that later. Now we gotta solve that. In order to solve that, we go back to that undocumented instruction. All right. The at sign is for initializing stuff. Yeah, execute only once. And then there's some other, oh yeah, the gen. So the gen instruction saves you lines of code for certain kind of signal kind of things, but it generates more power. But anyhow, we want to go back to this. All right, so we were spending 303. We should be able to get rid of, we'll keep it there for now. Yeah, actually we changed enough that we get rid of that. So what we're going to do is go at and then move 50. All right. And then show profiler. You see how it only touches a little bit. Why is this not happening? What am I doing different? All right. Let's see if this does it. No. All right. All right. So our lines of code went up. Not 31, but our best is still 29. So we just have to like lower that later on, but I'm not too worried. But look, now we can at least say, hey, our chip is more expensive. initially, but your power usage overall is going to be less. So that's how one thing that's how like one way you can market a chip. Um, Kind of like printers. Laser printers have a large upfront cost, but they're cheaper in the long run than inkjets. Inkjets are like super cheap to buy, but buying the inkjet things versus toner, the inkjet cartridges are just super expensive. And so it depends on who can afford the upfront cost and who can deal with the really expensive lifetime cost. So we can say this is the low power option. Um, but we are more expensive. We're $7 more expensive. Let's see here. So that's the next thing we could do. But while we're here, we can now say low power. And then we'll recopy that one. And we can be like, oh, do I want to work on saving us $7? That's quite a bit. Oh yeah, I can see I would save $7. So I guarantee you, Child Industries is using only one of these uh, to operate one set of these to do both things in music. Um, and I could see how I can do that. Um, it doesn't look fun. Um, and so because it doesn't look fun, I'm not going to do it. I'm going to let you guys work on how to make a cheaper version. So when it comes to the stats, the thing I tend to focus on more is low power usage. So the lifetime of the device is cheaper. The next thing I try to work on is low production costs. That looks like it's going to be pretty wow. There's a lot of people that got it down to 9 yuan, $9. Um, Child Industries is about here, and I'm just like overshot it big time. And of course, look, there's the power savings we could possibly get, and 17 seems to be about the average. Let's see, that's 20. 19. Oh, 17 is actually pretty low. Well, I don't know. I guess it's 10. Child somewhere around here. Less lines of code. Um, but I'm good with being lower power utilization on this one. Let's see here. Other ones were like, yeah, I still need to get better at. Let's see if this one. Oh, okay, so that's not one of my that has different types. I was just able to make one that has better power and cost. That was worse. All right, better. And yeah, I was able to do that with one device. Worse. All right. Yeah. I know I have some devices where I was able to succeed. All right, here we go. Um, Maybe this one device. I don't know. Usually I name them right. Uh, there we go. Let's go here. Uh, all right, here we go. I have a cheap one that could get me down to like super cheap. Well, same cost as my competitor. But the low power one, super low power, lower power than most of the drinking game scorekeepers on the market. Again, this is like one of the things I usually focus on. So um, that is Shinzen IO in a nutshell. Um, see here. It it helps you with, it gives you a puzzle, it gives you in the mindset of microchip design, not the design of the microchips, but um, electronics design, as well as um, the limitations you have. You have space limitations, you have cost limitations, power utilization limitations, and lines of code limitation. Um, and sometimes, like for instance, this one, um, I was able to make a cheap one that took up more power, or I could make a low cost one, or sorry, a more expensive one, double the cost, but lower power. There were several that I was able to make it cheaper and lower power with one package, but there are some where like, okay, I can only solve one of these, and which one do I want to go for? And that's one thing nice is that in the market, you don't have to decide for the client what is important to them. You can either make a cheap one and a low power one, and then sell both and say, hey, like, here's this, and then here's our low power version. And the client can decide which one that they want. They're like, oh, I really worry about, like, hey, I need to attach this to a battery. So I care about low power usage. Or, you know, I just want the cheapest thing on the market. Let the client figure that out. Anyhow, that's that's all for this uh, this game.